This YouTube is about a fuzzy dice accelerometer. So if you look at my sketch at the top here, this is the body of a car seen in profile. Here's the front window, this is the back window. And from the top of the window there is a single fuzzy dice that's hanging down with a string. It is at some angle with respect to the vertical. And so I have a sketch of it down here. And so here is the string going down like this. The car is accelerating to the right, which means the string has to be going back to the left. To understand the direction that the string has to take with respect to the horizontal, look at this picture right here. The string is backwards to the left, an angle theta with respect to the vertical. So if this is the vertical, the angle theta is with respect to the string and the vertical right there. And so this angle theta is the same as that angle theta. And the reason the string has to be back to the left if the acceleration is to the right is the only way that the string can supply a net force to the right is for the string to be angled upwards to the right. And if we take axes of y and x and we take the tension and we break it into a vertical component, t cosine theta, which has to balance mg downwards since there's no acceleration in the y direction, you can see the net force responsible for giving the acceleration in this direction from the horizontal component of t. So let's go through our typical Newton number 2 analysis here. So the Newton number 2 in the y direction is basically t cosine theta minus mg is equal to 0. There's no acceleration in the y direction, and so that has to be true. And Newton number 2 in the x direction is going to be t sine theta, and that's the only force in the x direction, is equal to the mass of the fuzzy dice times the acceleration in the x direction. And so from the first equation I can solve for t, and t is equal to mg over cosine theta. And then from the second equation I can solve for a sub x. Dividing through by m, I get a sub x is equal to t sine theta over m. And then substituting t in here, I get mg over cosine theta, that replaces t here, times sine theta over m. And as you can see, the m's cancel and I get g times sine theta over cosine theta. But you should remember from the previous slide, YouTube, that tan theta is equal to that ratio, and so we're going to therefore conclude that a sub x is proportional to g, but it's related to the hang angle of the string by the tangent of that angle. So let's take some special cases. If the string is hanging horizontally, that would correspond to a theta of 0. So this theta was 0, the string would be hanging, fuzzy dice would be hanging straight down. The tangent of 0 was 0, and so that would correspond to an acceleration to the right of the car of 0 meters per second per second. It could be going at constant velocity, but it could not be accelerating. If theta is equal to 45 degrees, on the other hand, you put tangent of 45 degrees into this expression that we have. Tangent of 45 is 1. And that would mean that if this string is hanging at an angle of 45 degrees, you have an acceleration of g to the right. So essentially, we have an accelerometer here. We can measure the theta of the string with respect to the horizontal, take the tangent of it, multiply it by g, and we get our acceleration in meters per second to the right. And essentially, if theta is less than 45 degrees, we have an acceleration to the right of less than g. If theta is bigger than 45, we have an acceleration to the right of g, to the right that's bigger than g. And so here's a question for you to think about. What a sub x is required to make the string horizontal? I'll let you think about that.